I guess we'll start by introducing ourselves. My name is Grant Skipper. I'm currently a PhD student studying under Martin Swaney.
My name is Dominik. I'm also a second-year PhD student under Martin Swaney.
My name is Zhixiang. I'm currently a master student advised by Professor that working on arithmetic multiplication.
Be confident.
Yeah, my name is Taufique. I'm a first year PhD student, and I'm working with Professor Juliette.
Yes.
I'm Tessa. I'm a second year PhD student working with Martin Swaney.
Juliette. I'm also a second year student working with Martin Swaney.
Okay, so today we'll present on our FPGA project for this class. So we're going to be doing a FPGA network performance infrastructure, and we're going to talk a little bit about what that means and what the kind of problems we're trying to solve. So when it comes to network performance, a lot of the things that you'll see, like when you do like a ping, what that entails is copying some data from memory into kernel space and from kernel space into a ring buffer throughout the NIC. So what happens there is you end up having a little bit of overhead that isn't usually discussed when it comes to network performance. So an example of this is for like a really high throughput link, like if you've heard of ESNet's perfSonar project, if you ever use iPerf. Sometimes you might have the kernel send a packet and the receiver might actually receive it before the kernel even realizes, the user space program realizes that it received it. So this causes issues when it comes to accurately measuring your network performance. One of the things there, one of the big challenges with network performance monitoring is time synchronization along clocks. So you guys may have heard of NTP, which is Network Time Protocol. So clock synchronization is a very important aspect of network performance, I guess measurement, and we want to try a way to offload this problem onto hardware.
Yeah, so one of the key things to consider if we operate from the user space and we send a package through the NIC to another node and back into the user space is that we travel a whole bunch of layers which add a whole bunch of latency, and in most cases where we do not employ any non-zero copy techniques, we end up copying the package through multiple buffers until it exits the network at the end. And this means that if we just use ping or iPerf to measure the latency, is that we add a whole bunch of system noise, which then decreases the accuracy from nanoseconds into milliseconds, which may not be accurate enough if we try to get a reasonable baseline performance for a complex model. Also, if we're trying to measure the time in one direction, we have the issue that we operate into different time clock domains. And one way to circumvent that is to do a round trip time measurement and then just divide by 2. We will talk about this later in our implementation of an FPGA.
So one of the works that we looked at was open source network. It's this open source, OSNT is this open source project for network monitoring made for NetFPGAs, which is where we kind of base our work off of. So OSNT isn't exactly trying to accomplish what we're trying to accomplish here, which I guess we'll get to in a second, which is essentially measuring as fine granularity as possible, leveraging the FPGA platform with the PS to get an accurate measurement of a packet. But OSNT is kind of a stack of open source FPGA designs for making sure that your network performance on your FPGA is working correctly. So they do implement a little bit of the structure that we're going to be talking about implementing today. It's very widely used, or not widely used, but so there's a paper that we refer to it on. I guess there's not much to say out of that.
Which is about the log-GP model. Now, the log-GP model is an extension of the log-P model all the way back from 1995, which is a more detailed view into modeling the network performance beyond just simply an alpha-beta model where you model the latency and the bandwidth. I really like this model because it also encompasses the overhead as a parameter of sending and receiving packets. And also it uses a parameter G, which is the minimum gap between two messages, which is bound by the underlying NIC hardware. And as we can see, just by sending multiple messages, the gap is usually much higher than the overhead, which means in that case we're no longer bound by, the overhead is no longer the bottleneck. Whereas if you only send one package, then the overhead definitely comes into play. And our goal is to use this model or to get a good empirical value for this overhead, and then try to use and verify this model, or potentially even extend it. Oops.
Oh, sorry. Go ahead. Do you want to talk about our setup? Okay.
Yeah. So the way we are planning to implement the project is there will be a packet will be sent from the OS, and it will go through a programmable logic, and from the programmable logic we will be keeping a like timestamp, like from when like this packet left the machine, and it will be a bit later than the OS because OS has some overhead, and when the the ping will be returning, so it will be returning again through the programmable logic first, and then go to the OS, and we will be take the timestamp of that moment, and write it on the direct memory access. Okay, and then when the OS will receive the packet again, it will then again measure the time difference of its own, like when it left and when it received, and it will then read from the memory the exact time that it that was calculated by the programmable logic, and from there we will be able to analyze that. Okay, how much improvement was made if we measure it in the OS level or the programmable logic level. And
these will be the boards that we're developing on, these ECU102s. It has a Xilinx 7 series FPGA on it with an ARM Cortex A53. The ARM Cortex A53 is where the Petalinux processing subsystem will go, and everything will have to pass through the PS. So this is kind of like a high-level design of what we are trying to accomplish here. Like Taufique said, we have our programmable logic here that interacts with the ARM64 controller here, which is going to be running Petalinux. So all egress and ingress traffic will have to go through the programmable logic. If you're familiar with the, I guess, Xilinx stack, everything passes through AXI. So all we really need to do is we need to hook on some programmable logic here that has to incorporate, like Taufique said, the clock and timestamp logic to mark those onto the AXI stream that comes from the ARM64 controller that goes out and inside the Ethernet. And then from there, we can DMA that into memory, and then lock onto those memory addresses with some UIO so we can read from them and then compare them. Is there any questions on this? Because I know it's, we can probably go into a bit more details if you guys are too clear.
So you try to reduce the overhead of the operating system?
Yeah, so we're trying to measure that overhead as well.
Okay.
Because this is a good platform to measure this, because all of the traffic has to go from the controller through the PL to hook onto that hard IP, that Ethernet MAC IP that Xilinx provides.
So the operating system is actually running on the ARM core?
Yeah, so the operating system is running on the ARM core, the Petalinux OS, which is Xilinx's kind of standard OS. And when you instantiate, or when you want to run Petalinux, instead of running like a bare metal program, you have to instantiate this core called the Zinc processing subsystem. And that kind of controls how the ARM core is allowed to interact with the peripherals on the board. So that way we're able to latch on that AXI string out of the PS, the processing subsystem, out to the Ethernet MAC, which you can instantiate to actually send traffic out the physical device. So that way, it's kind of like man in the middle in between the processing subsystem and the actual physical Ethernet MAC, the PHY. So we can measure both when the OS sends it out and then when it's actually going out.
So who will generate the network traffic?
So we'll get to that.
Okay.
We'll
But
talk about that later.
we will have some software components we'll talk about that are going to help facilitate this. And these are the components that we kind of bust over really quickly. So you have your Ethernet 10 gig MAC, which Xilinx offers. These QSFP plus ports will go through 10 gig in Ethernet. Then we have these Mellanox 10 gig NICs to actually communicate with them if we need to, and we'll have them sent out to a host. The Zinc processing subsystem, which sits on the ARM Cortex A53 controller, the DMA and UIO, which is essentially we want to get a packet, we want to mark it, and we want to write that to memory. So then the kernel, you can write a user space program to memmap that address space and then read from that address space and see what the programmable logic marked it as, and then see what the OS marked it as and compare those differences. And one of the challenges there, like you mentioned before, is that network timing. So like the PL's clock and the PS's clock are different. They'll be running at different speeds. But it should be pretty trivial to just adjust for time since we know what frequencies they're at to see what the actual real relative time difference is. But the bread and butter of the logic, I think that the actual DMA, UIO, and sending out packets is probably the easier part. The bread and butter is finding out the efficient ways for stamping and hoisting those up to the kernel. So what of the packet we want to measure, what clock rate we should use for the most granular measurement that makes sense for our project, and what the proper way to use a clock in PL is. I've never touched that. I think that's what Taufique will be working on and a couple of our other group members. And this is a previous design I had worked on a while ago. So Dominik and I have a lot of experience with hardware design, especially for the network. This is what it would look like if you have this open in Vivado. So here's your Ethernet MAC IP that you can instantiate from Vivado. So this would actually be communicating with the PHY to send something out. This would be the Zinc processing subsystem that you'd instantiate that would talk to the ARM controller. We have, from the Zinc Ethernet MAC, we have an AXI stream broadcaster, which can go to our own logic here, which would be like our clock, our parsing, etc. And also broadcast to, it's essentially a stream splitter to go to the processing subsystem. And there's a DMA block here that we're going to use to communicate with the PS. And that's also used for getting stuff from the PS to Ethernet MAC. You want to talk about the software?
Software. In this project specifically, we are going to develop four softwares. The first one is that we will develop a client and server program to generate network traffic. The first we are going to try the IDMP protocol, and then we will see whether we can customize it to in order to have a better measurement. The second one is we are going to use the HD. We are going to write a program. We are going to use HDR to process the stamp in the UIO interface to the PR into the user space to read the DMA data from the and finally we are going to develop a program to automatically collect data for the analysis purpose.
Is it not working?
Oh yeah.
Sorry. Juliette.
So the goals of this project is, well, I should probably mention that the Sweeney Lab is dedicated to improving network performance. Essentially, if you do any kind of supercomputing, any large calculations on a cluster, one of the best ways to speed up your results is by improving network performance. So that's why we focus on things like this. These tools, sometimes they're meant to be, as Dr. Sweeney says, a bump in the wire, doing calculations across the network just to reduce load. So in this particular project, we want to create a base network performance tester in order to get granular measurement of an unimpeded 10G link. In other words, we want to measure its link throughput and see if there are things that we can do to improve the performance. We also want to see what the overhead cost is. Now it's more difficult than you would expect with things being so low level. In your operating system, there's tons of other processes going on. By the time you go from network card up to the application layer where you might be doing some performance testing, you can lose a lot of time. And also the time measurements can vary significantly. That's something we want to avoid, and we think that with the FPGA model and the hardware, we might be able to do a better job of that. So we're going to take a particular base case to experiment with and test other configurations to see the relationship between overhead and network delay, and sort of dive into that a little bit. Something that's normally opaque here, since everything is so low level and stripped down, it's much easier to see what's going on. We hope.
And that base case would be a single packet, for example. So just measure that difference between a single packet for the difference between the OS overhead and the FPGA the hardware timestamp. And then from there, once we get that working, I think that there's a whole lot of other experiments we can do. We have some hardware for introducing network delays into the link. We can saturate the link and see what the overhead looks like. We can try to bloat the memory space that the kernel's operating on and see if that has any performance. So there's a lot of different ways we can take this, but the focus for right now is to get this first base case going. Dominik?
Yeah, whenever when you are working on the FPGA, one of the first things you want to do is that your module are working correctly. So a preliminary test case would be just to test the logic in simulation, and once that one is working, we need to build a small micro benchmark in the PS. We then generate the package, sends them over, and essentially measures the user space timestamp, but also extracts the FPGA to FPGA timestamps that logic adds into the payload, and then simply compares the two and generates some nice looking plots.
There's more than one way to generate sort of plots, of course. You have your typical hardware models, but you can also use things like differential equations to model the system in a more abstract way. So it might be interesting to see if the two line up.
And in our implementation, the packets that we send out will most likely, I think we've looked at using either ICMP or just some custom Ethernet layer packets that you can just send out over the socket layer. That way you can send out like a packet ID and then a packet timestamp, so you can just parse the payload out and you have those two values to hook onto to identify the packets. Because if you just send any random packet, it's not worth the time to implement TCP and PL.
Also reduces or controls the overhead so we can get more precise measurements.
Yep. So I guess the big components of the project are, of course, the software we just talked about, like a client server for sending the packets. The Verilog we'll need to use to write the RTL for our custom logic that involves the timestamping and parsing the packets and hoisting them. I know, at least I need to look at micro benchmarking kernel space processes more closely, but I think Dominik has actually a lot of experience with that, with his supercomputing experience. Then we hope to show you guys, or we plan on showing you guys a demo, hopefully of some really cool experiments, but at the very least we'll have our base case going, and we can set that up pretty easily in the classroom for presentation.
And also, last but not least, of course, our performance results. Here is one plot that I'm already interested in, which is the delay bandwidth plot. As you keep increasing the packet size, what's the delay that you're measuring? And one of the hypotheses is that the user space to user space performance is increasing exponentially, because as the packet size is growing bigger, more time is spent copying that buffer from buffer to buffer, whereas from FPGA to FPGA, technically there should be a linear scaling. So we hope to see two curves, and then the area in between marks the OS overhead, which is a function of at least one parameter, which is the packet size.
Can you briefly describe who will charge what? Who are in charge of what in
Come
this?
to that
Okay.
at the very end.
Yeah, I guess we can get to that now, I guess, because this is our working schedule. It's not too granular yet, but there's not much to be said there. But who's in charge of what? So I think all of us will be having a hand on different software aspects, and the software aspects may change as time goes on. It's just the thing. Do you want to walk through this, I guess?
Okay. So I'm testing MIT group I'll be probably helping him with the packets and perhaps custom interface. And I also be writing papers for the project.
And let's see, Dominic and I will probably be handling a lot of the PL stuff, but we're trying to get a group as incorporated as possible with writing PL, help them learn. I believe Taufique will be taking care of the clock logic, right? So we're still in the process of delegating, but we have a rough idea of what aspects of the project we want to really focus on. And I think that's our last slide.
So you will do the PETA Linux.
Yeah, I'll get that set up.
Okay.
Is there any questions?
No, I'm good.
Okay.
Is everyone still breathing?
Awesome. Well, thank you guys.
Questions, guys?
It's okay.
If no, let's thank our speaker.